Welcome again to another adventure in KDM. This time we are going to be doing a problem that involves a graphical solution to a static force problem. In it we have a 4-bar link labeled conventionally O1, O3, B, and C. The lengths of the sides are shown here, and it's superfluous, but here is the speed with which link 1 is rotating. And say it with me now, if this is showing positive, given our normal direction for rotations and for axes, which would be x and y like this, the angular velocity is always about the z-axis, and a positive direction will be counterclockwise. So let's get started. As with any dynamics or statics problem, the way to approach this is to set up free body diagrams for each of the bodies. Now, in this case, we have the rocker, the coupler, and the crank. We are applying a force, P, and I'm going to arbitrarily set it to be equal to 10 newtons. And what I would like to know is what torque do I need to apply to my crank, labeled T sub 1, in order to have this body be in static equilibrium. So we will start out by creating a free body diagram for the rocker. In order to create a free body diagram to scale, I'm going to use a couple of triangles to transfer this body in its correct orientation so that I can draw it in isolation. So there's my line. It is parallel to the rocker. The rocker has a length of 20 millimeters, so I'm going to mark this out so that I am drawn to scale. 20 millimeters, pretty close, but not quite. And I'm also going to transfer over this force line, again using two triangles. And what I really ought to do, I suppose, is figure out exactly where the body that falls. So I'm going to use my compass and set it to that length. Looks like right about there. That's where the line intersects. And I lay a triangle atop that vector and slide it over until I can draw a line in. This says it's 10 newtons, so I'll go ahead and set the length of that vector to 10 millimeters. So, what I've done so far is draw O3C with a vector to the correct length, P. Now, in order to have this particular portion of the mechanism be in static equilibrium, I know that it must fall within one of three different setups. This could be a 2-force member, a 3-force member, or 2 forces in a couple. In this case, looking at the initial mechanism, it is definitely a 3-force member. I'm going to have a force coming from the coupler link and a bearing force coming from the ground. So, the 3-force member, we need to recall that those 3 forces intersect at a common point. Because the coupler is coming at an angle, and because it's the only thing that is contacting at point C for the rocker, I know that one of the forces that will be applied to the rocker is coming collinear to the coupler. Its line of action will be the same as the coupler. So, again, I am going to use my triangle trick and set up my force vector at point C, and that will be the direction of one of these forces. I don't know quite how long it is, I don't know what size it is, but that gives me the direction. Because I know that for a 3-force member, the 3 forces must intersect at a point, I can extend the vectors here to reach a common point, and then that will define the direction of my third vector. So in this case, I can extend vector p, and I have an intersection point. Therefore, I know that the line of action of the force acting at bearing 03 is like this. So, given P running up and to the left, force coming from the coupler, which I will label force 2, 3, as this is body 1, body 2, and body 3. And then I will also have force 03 with this line of action. So, what I can do now is a vector addition. I have this force P drawn to scale. So, I can set up, again using the triangles to transfer things that they're parallel, just a little further. This is kind of a bit of a learned art for the triangles. So, within a reasonable degree of accuracy, I have just created a force triangle that should give me magnitudes for each of those forces. So, I had scaled force P at 10 newtons, it's 10 millimeters. Therefore, force 2, 3, which is represented by this line, if I measure it, I get about 7. So, force 2, 3 is approximately equal to 7 newtons. Force 0, 3, measuring, is approximately 9. So, force 0, 3, 9 newtons. Now I'll call a brief halt and move to the next video file.